Let me just start by doing something that may be less common in the US, but is fairly common in Canada. And that's actually acknowledge that most of the work I do occurs on lands that were originally settled by indigenous cultures. And so I work from what is called Treaty 6 territory in Canada. I think it's important for us to at least reflect on the lands on which we actually do our work, or especially in astronomy, where we have our facilities. I know that may not be as popular in the States right now, but hopefully it's something we can work towards understanding throughout our field. So normally when I talk about multi-wavelength astronomy, I have to explain the electromagnetic spectrum, etc. When I talk to a high energy group, I often know how to do that because I think inherently a lot of what we do is multi-wavelength. But what I do like to remember is sort of some of the regimes that we live in. At the longest wavelengths, radio, submillimeter, we're often talking about emission that's either coming from synchrotron radiation, free emission, or molecular lines. And here, the type of science that you're going to get in high energy astrophysics is often jet science and shock science. When we go to sort of the UV optical near IR, you're often talking about black bodies at the temperatures of stars, atomic lines. So often in high energy astrophysics, we're talking about stellar science and science of the cooler parts of accretion disks. And of course, where most of us are in our basis, up towards the X rays and gamma rays, we're often talking about things like high temperature black bodies, optimized photons, and highly ionized atomic lines. So things like hot accretion science, hot gas science, and particle acceleration science is often what's dominating our fields. So I looked back and I was trying to do this review talk and I was trying to come up with all the multi-wavelength astronomy high energy highlights. And there's too many of them. Our field is intrinsically, I feel, multi-wavelength. Things like the natures of bright X-ray sources, the masses of compact objects, the nature of novae, which we'll hear a little bit about later on, the critical role of the disk instability mechanism in controlling how viscosity changes and we get accretion onto compact objects, gamma ray bursts, high magnetic field neutron stars like magnetars, and my personal favorite, the connection between accretion and outflows. I am going to give you a bias that is largely coming from my studies of X-ray binaries. And one of the reasons why I think this is a good region to sort of think about for multi-wavelength astronomy is we essentially have all the different types of science that I talked about for multi-wavelength astronomy in one object. The donor star is often in the optical UV, the accretion disk is in the X-rays, and when we have a relativistic jet, that's often in the radio or submillimeter. And so a lot of my job and the job of many of the other people in my field is piecing together this puzzle using multi-wavelength astronomy for X-ray binaries. I'm not just going to talk about X-ray binaries in this talk, though. So if I think about how multi-wavelength astronomy normally works, the first thing we have to do, and often the most critical thing we start with, is identifying counterparts, which is intrinsically multi-wavelength astronomy in much of what we do. Although with AXIS, we'll have the ability to get such precise positions that we won't necessarily be needing to do that to get the X-ray position, but it's more to understand what's going on at the other wavelengths. Then, of course, we work on understanding the class properties, all to constrain physics. And the other part that I think we do as a field that is the profitable bit is developing the next generation of scientists. So I will say for the younger or earlier career people in the field, I have some slides that are more text walls. I'm going to skip over them in here, but feel free to download the slides in case you want to know some of the names that you actually need to be looking out for some of these fields. So I'm going to start by talking about one of the foundational objects in my field, which is Cygnus X1, and how we basically have shown that multi-wavelength is critical for identifying the counterparts to high energy stellar sources. Of course, Cygnus X1, its very name suggests it was discovered early in the field of X-ray astronomy in 1965. But if you look at how we actually learned what this object is, it's this story of getting better and better positions, first in the X-rays, where we eventually got a position down to 1 arc minute. And then when we had a radio observation that localized the core jet of Cygnus X1, where the actual binary is, to 5 arc seconds. And almost you have years between the X-ray stuff, we get a precise position, and almost immediately we know that there is a supergiant star in the same position. You get the supergiant star. Almost immediately, we start getting radio velocities and optical. And from there, and what we understood about supergiant star masses at the time, it implied the existence of a dark compact object. And the mass of that compact object depended critically on the distance. And for many decades, or for at least 15, 16 years, so that's not many decades, arguments ensued about what the distance was, and there was even the famous bet between Hawking and Thorne about whether SIG X1 was a black hole, which was conceded in 1990, but that was well before we actually had a really secure distance to SIG X1. And I will tell you that secure distance is one of the most critical things we do in astronomy. If you fast forward now to the early 2000s, using radio interferometers from across the US, the long baseline array, we were able to measure the position of the core close to where the black hole is to about 0.1 milliarc second positions, and over time build up the proper motion and the parallax, where we got what seemed like a fairly precise distance from a parallax that was about 6%. Good precision. It turns out that there was some issues with the accuracy, but once you had that good precision, that precision almost instantly led to a mass. And so we have the idea that we actually have a fairly massive stellar mass black hole in SIG X1 of around 20 solar masses. It turned out that the initial position parallax was slightly off, and both Gaia and some refinements of the radio position have actually gotten it to be more massive, which has some interesting challenges for how the most massive stars lose mass, and the fact that we overpredicted how much stellar mass loss was. So I wanted to go through the history of SIG X1 rapidly to really emphasize that need for good angular resolution and putting together the multi-wavelength picture. Because basically SIG X1 now acts as one of our stereotypical pictures of a stellar mass black hole. I'm not so sure how stereotypical it is, but it is at least one of our two sort of standard stereotypes in the field. And it's often used as an analogy for supermassive black holes, where we hope that mass scaling will help us bring our understanding between the fields of X-ray binaries and AGN in both directions. As a side note, during this, we learned a lot about relativistic X-ray binary jets. We had the first discovery that on milliarc second scales, what we're seeing are sort of one-sided, very relativistic X-ray binary jets in the radio. And these days, we're actually can look at the propagation of jets in the X-rays. So this is some recent work with a known black hole that erupted for the first time, at least in the lifetimes of most of us here, or I think all of us here. And we literally, not just in the radio, but also in the X-ray, can see the position of the knots as they come out. And this is actually important because we're starting to measure things like how these jets are decelerating and understanding what's going on in the environment around the X-ray binaries, which is helping us tie together some important things about feedback and hopefully, again, applications to the more massive black holes and understanding things like eventually, baryon loading in jets, etc. This is a field where I think AXIS can do a lot of good work with target of opportunity observations. I'm going to quickly talk about some of the other fields in compact objects where identifying counterparts were important, but if only to highlight some important lessons. So I'll actually start with the lesson and then just comment briefly on some of these objects. The first lesson I want us to remember is that surveys made years before future observations can actually drive new discoveries when cross-matching. So let's think about Cas A, classic supernova remnant. Cas A was first detected in the radio, well before it was detected in the X-rays. There's actually some possibility that Flamsteed, back in the 17th century, saw an optical transient associated with Cas A. There are arguments about this, but we believe that this is actually what occurred. On the other hand, other supernova remnants are clearly identified with historical transients, often from Asian records. Now, that's the most extreme form of a survey back in the ancient times affecting our knowledge now, but I think that applies even for surveys made today for instruments of tomorrow. When we think about gamma ray bursts, this has really been a triumph of multi-wavelength astronomy within compact objects and stellar remnants. The lessons that we're learning these days is how important rapid response is becoming. And it's not just important, but it's also becoming more rapid over time. So what I will say is that Axis is already very well suited for this with the ideas of rapid response built into the instrument. And of course, the new kid on the block is multi-messenger. I think it's going to be critical in the era of Axis for identifying counterparts to multi-messenger sources and understanding back and forth the multi-messenger world and the astronomical world. And of course, one of the ways in which this occurred was with Swift and its ability to automatically slew to gamma ray burst when its wide field detector detected something going on. And there have been some incredible discoveries, not just in gamma ray bursts, but also in X-ray binaries because of this automated abilities. So just as a quick reminder, long gamma ray bursts we know are associated with core collapse supernova, again, because of the positional counterparts. And eventually we started breaking down transients, not just for spatial coordinates, but temporal coordinates. And coincidences that occurred first within a day, what I like to call quasi simultaneously, and then within like 1.5 hours. Still not strictly simultaneous, but close enough. And of course, these days with the multi-messenger, we know that short gamma ray bursts are associated with kilonova and neutron star mergers, or at least most of them are, we think. We heard a bit about magnetars yesterday. I just want to focus on some aspects. Very fast timescales. We either need you to have an instrument that reacts faster than physics will allow, or it needs you to have a large field of view with sufficient sensitivity for discovery so that you can take advantage of serendipity. And CHIME is a great example of that. It's a broad survey by a relatively large grasp instrument, and it balances against needing very fast response times by just thinking, how do we take our data better? But in order to do this, automation is very much needed here. And I honestly believe that as we think about the next generation of facilities, automation is not just a key, it is the key for us getting the most out of our work. Now, when we think about what we've learned from magnetars, of course, we talked a little about this yesterday. You know, we had the ability that we started identifying magnetars with pulsars, but these days, the most exciting things I'm finding are, as we talked about yesterday, the fact that some magnetars seem to be associated with fast radio bursts. And we had basically fast radio bursts is one of the most burgeoning fields. I'm not sure if I put it in stellar remnants yet or not, but at least in radio astronomy, it's one of the most burgeoning fields. I also want to mention that there's some possibility that the faint blue optical transients, the F-bots, may be associated with magnetars. We don't know that for sure. AT 2018 Cow has some claims that it was could have been associated with it. And there's another source as well. These things go back and forth. But we have a lot of new forms of transients where by identifying counterparts, we're finding out lots of information for it. And finally, I want to talk to you about a new class called pulsar likes, or at least that I'm calling pulsar likes, because they highlight the need to look in unexpected or formerly discarded phase spaces in our field. So there have been two new classes. One have been white dwarf pulsars. So this is a picture here showing pulsations in optical and in radio. There are pulsations actually across the multi-wavelength spectrum from what was originally assumed to be a cataclysmic variable, AR Scorpii. And nowadays we call this a white dwarf pulsar. It's not the only known white dwarf pulsar. There are a handful of them. At the same time, we've also been finding what are called long period pulsars or ultra long period pulsars, depending on who you talk to. So this diagram here is the standard PP dot diagram you see for pulsars. And most of your pulsars are the things in the lower left-hand corner Your magnetars, sorry, that lower left? Yep, lower left. The magnetars are in the upper left-hand corner, and you'll see commonly a line in these diagrams. This line is called the death line. We basically think that pulsars sort of decelerate down to this death line, and we shouldn't see anything beyond them. But in recent years, we've been seeing objects that pulsate, especially in the radio, beyond this. So in addition to the white dwarf pulsars, we also have some ultra long period pulsars that have been recently discovered. We don't have good PDOT measurements on these yet, but these are clearly in the beyond the death line. And if you look at the periods, one of the reasons why we're just discovering them now is because no one looked for them. It's not that they weren't bright enough, it's just that no one expected that you would have, you know, tens of seconds, or not tens of seconds, sorry, hundreds of seconds, thousands of seconds periodicity in the radio. So now I'm going to move on from the idea of identifying counterparts, which I think is absolutely crucial, to some aspects of understanding class properties. The overall lesson I think is learned from understanding class properties is that you need large samples and you need systematic approaches. The other thing is that we need a lot of coordination between our multi-wavelength and multi-messenger facilities in order to do some of this work. You sometimes do this work on specific objects, but eventually you want to do this on a large number of objects. The problem can potentially be if you need strictly simultaneous data, or what I like to call delayed simultaneous data, where you're trying to track the same physical phenomena, but there are actually physical time delays that you need to worry about. So that is something to think about as we build the next generation of instruments. How do we build in coordination for strict simultaneity, given all our limited resources? So if we think about one of the most important things we've learned about for compact objects, I think it's actually their masses. This is how we figure out what some of these compact objects are. The X-ray binaries were our first glimpse into the masses of black holes. And we have a diagram where we're hugely proud of the fact that we were the ones getting black hole masses. And as you can see, there's a large part of this diagram that's blacked out. At the same time, a little less multi-wavelength, as this often came only from radio, we had masses for neutron stars. But one of the big revolutions has been using gravitational waves to measure both the pre-merger masses of two objects and the post-merger mass of the combined object. And unfortunately, in the electromagnetic world, we're now dwarfed by the number of binaries that have been found with gravitational waves. But the other thing you'll notice is that there is this sort of difference. The gravitational wave sources seem to be more massive than the electromagnetic sources. Is this a selection criteria, or is this physics? I would say that the jury is still out on which one of these is actually going on here. Clearly, the post-merger masses are going to be more massive. But even if you look at the pre-merger masses, we tend to see much more massive black holes than most of the stellar mass black holes done electromagnetically. If we want to think about true multi-wavelength work, I spent a lot of time thinking about accretion jet coupling. And a lot of this work was first done with Cygnus X1, which forms a non-negligible part of the point on this graph you see here, which is showing the radio pseudoluminosity, really nu L nu, versus the X-ray luminosity. And in the beginning, there was this nice correlation. The correlation corresponded to some physics. You could mass scale this up to supermassive black holes with the fundamental plane of black hole mass activity, and things were great. This is the picture these days. It's a lot less clear. There are potentially multiple populations. We argue about this for the black holes. The neutron stars are clearly less luminous. There's more going on, but inherently, in order to understand this, we have to combine radio information with X-ray information. Initially, the data weren't particularly quasi-simultaneous, which for transient objects is a problem. So these days, we really push for quasi-simultaneity within a few days, or strict simultaneity. The other thing I want to point out here is the relative scarcity of objects at low luminosities. When you get to X-ray luminosities around 10 to the 31 to 10 to the 33 ergs per second, you're talking about sources in quiescence, where most of the X-ray binaries actually are. Axis can clean up here because you don't necessarily need to do planning for Axis. Instead, you try to get the radio data when Axis is looking at a field with known X-ray binaries. And we actually get down here fairly easily because we are so sensitive with Axis. Basically, Chandra's been one of the main instruments we've gotten to pick up the objects that are in the lower bit. I don't know if you can even see that. The lower left-hand corner. But I'll also say that we've moved on. We not just X-ray binaries, but increasingly we're looking at how accretion and jet coupling may work in white dwarfs. White dwarfs, despite what you may have been told decades ago, are radio emitters. They're just not particularly bright, except for a few sources, including the one that we start was stereotypical SS Sig. This is stuff that you can do with entire populations, but you can also do great stuff by looking at individual objects in detail. And I'm sorry to bring up stuff that's related to groups I'm involved with, but I thought this was really important for thinking about Axis, because this is work where we combine X-ray, optical, radio facilities all at once, because we're combining multi-wavelength, we're doing imaging, we're doing light curves, we're doing SEDs, we're doing spectroscopy in most of the different ranges, and we're doing timing, all to create massive explorations on a single object. So what you see here is data from an X-ray outburst of the black hole X-ray binary MAX CJ1820 plus 70. In the upper left, you have the break frequency in an SED diagram. So we have measurements over the entire SED, and we're measuring how that break frequency changes. That tells us potentially a lot about jet physics. We have on the upper right, we have the X-ray photon index. On the lower left, we have the disk temperature from X-rays. And the lower right, we have the radio to X-ray relationship. In the background, we have the accretion states, which are coming from the X-ray information. And I hope you can see, without talking about the detailed physics that's going on here, there are clearly correlations between the accretion state and what's going on in the jet. And if I do one thing in my career, it's to help us understand how and why jets are launched. This is the type of work that you could potentially do. But it's not just this stuff, with this type of raw timing. We're also looking at timing within observations. And we're looking at now a power density break frequency and how that may change as a function of the electromagnetic spectrum all at around the same time. And if you look at where the break frequencies are for the highest frequencies, they are at things that Axis can actually get to. This work needs strict simultaneity. But the other thing here, this is just comparing the cross correlation function of radio with radio, looking at about 26 gigahertz and about 8 gigahertz. And what's going on here is you're looking at the optical depth one surface of a jet. The higher your frequency is for the synchrotron emission, the closer to the black hole that you're looking at. So you have a physical scale difference here that you're getting with these time lags. This time lag for about a factor of 3 in frequency is on the order of minutes. So if you have synchrotron emission and you start scaling this up every factor of 3 frequency up to get X-rays, if there is synchrotron emission in X-rays that you think might be associated with the jets, big debate in the community, the time scales now become fairly long that you no longer just need strict simultaneity, you need delayed simultaneity. You need to actually think about the fact that your lower frequency observations need to occur after your X-ray observations. So what I'd like to end with, this is just sort of a sampling taste because 25 minutes is nowhere near enough time to even go into depth for one of these fields, is I want to talk about what I see the Axis strengths are within multi-wavelength astronomy with a whole bunch of quotes that I hope are memorable. We all know that the sum is greater than its parts, and I think that's the true strength of multi-wavelength astronomy. The future is now, but I think the future is based on surveys. So now we have surveys like VLAS and RAX. We have arc second to a few arc second localizations of radio objects across the entire sky. Most people don't even seem to understand that that's sort of revolutionized in our field. We've got large surveys with Euclid. We've got all sky surveys with Gaia. We have eRosita, but we have a huge treasure trove of all sky surveys to base Axis stuff against. In the future, we will have things like SKA, NGVLA in the radio, Rubin, the very near future, in the optical, LISA, Axis. And I also want us to think about things like the Cherenkov telescope array as we go up to gamma rays. I don't have nearly enough time to talk about that, but that's a whole nother exciting field that is really going to burgeon over 2030. I want us during Axis years to move fast and break things. And my idea of moving fast is largely with the rapid response. And the thing I want to break is our understanding of things, not the instrument. Let me be clear. No spinning to death. Multi-messenger is the way. I don't think that's a surprise to this community. TDAM, and then the multi-messenger part is really what I think is actually capturing the imagination of many people more than the deluge of astronomy information we're going to get from Rubin. But I do think multi-messenger is the way for 2030s to 2040s. Luck is what happens when preparation meets opportunity. Famous quote by Seneca, or at least attributed to Seneca. Our preparation is having broad surveys that take advantage of the high grasp of Axis. It means looking in unexpected phase spaces. It means doing ... whatever preparation we can do now to take advantage of that relatively big field of view for X-ray with great localization. And of course, teamwork, guys and gals, and everyone else. We got to work together. A lot of the stuff I do in multi-wavelength requires large teams by some X-ray fields, not as big teams as particle physics, but 20, 30 person teams across the electromagnetic spectrum, lots of different facilities. And what I'll leave is just some of the multi-high energy puzzles I think Axis is going to be helping us explain. But I basically stopped here because I ran out of room, not because I ran out of imagination. Thank you very much, and I'm happy to answer any questions.
Okay, we have time for questions. Yes. If you could go to microphone, yeah.
Nice talk. Given how important the multi-wavelength counterpart is, I want to ask your opinion on what to do when it's difficult to get the correct counterpart. Like, for example, with eRosita, the X-ray positional uncertainty is rather high compared to Chandra, and you match to multiple optical counterparts. So what do you do to figure out which one is the true counterpart? Or alternatively, when you look into, say, globular cluster, when there is the optical source is much more dense, what do you do then?
Well, yeah, globular clusters was a particular passion of mine in my PhD, and still to this day. But I think a big thing that we are working towards in astronomy is not just the idea of counterparts, but probabilistic counterparts. And this is something that you can do particularly well when you have multiple central counterparts in the field, using a bunch of the different information and a lot of hard work. You can start to say, I think there's a certain percent chance that this is the counterpart, a certain percent chance this is the counterpart, etc. That's going to be good for large surveys. If you're thinking about a single object, then basically you have to take advantage of the fact that most of the time, multiple counterparts are going to be in a single field of view of most instruments. So at least you're getting information on all of them, and it will take a lot of work to put together the picture to go from a probabilistic counterpart to a absolute counterpart.
All right, thank you.
Other questions? Going once, going twice. Well, let's thank Greg once more. Good on Zoom. Okay, great. So our next speaker is Temim, who talking about supernova remnants and progenitor systems. So
Thank you so much, and thank you for the opportunity to give this talk. So we, of course, know that supernovae are important for virtually all areas of astrophysics, but there are still fundamental questions that we don't understand about the explosions. And one of these questions is what types of progenitor systems produce the supernovae that we observe and how they explode. And one way to probe this is through observations of supernova remnants. And these are the nearby remains of supernova explosions that bear the imprint of the explosion and can remain visible for thousands of years. So today I will give some examples of how multi-wavelength observations and X-ray observations in particular can be used to understand supernova remnant evolution, their progenitor systems and the explosion properties. And I will of course highlight the type of advancements that AXIS would bring to this area of study. So there is an excellent AXIS white paper by Samar and colleagues that outlines the incredible advancements that AXIS would bring to the study of pulsar wind nebulae and supernova remnants. I have listed some of those broad topics on this slide, and a number of these topics will be covered by other speakers later in the session. So with the time that I have today, I have decided to focus on the topic of supernova remnant explosion and progenitor properties. And what I will concentrate on supernova remnants that host pulsar winds. This is something that I am particularly interested in. And I want to mention that this talk will not be a review. There is really no time to cover all of the work that is being done in this topic. But what I will do is give some specific examples of the types of methods that we use in X-rays to understand the progenitors of supernova remnants and something about the explosion that produced them. So the variety of the core collapse supernova types that we observe are broadly divided into type 1 and type 2 explosions, and this is based on the presence or absence of hydrogen in the optical spectra of supernovae. And these supernova types are broadly related to the mass loss that a progenitor experiences prior to explosion, and whether the star's outer hydrogen and helium envelopes are intact when the star explodes. And the standard view in the past used to be that the more massive a star is, the more likely it is to lose its outer envelopes through stellar winds or mass eruptions. But now we understand that a star in a binary system can also experience this envelope stripping. So now we understand that it could actually be a wide range of masses that can produce stripped envelope explosions. It could either be a very massive star through stellar winds or lower mass stars that are in binary systems. So what we want to understand is what type of progenitor properties drive the diversity of the supernovae that we observe extragalactically. And basically, do the core collapse supernovae arise from distinct types of progenitors, or is it more of a continuous distribution? So in my research, my approach has been to probe these questions through studies of supernova remnants. And the reason is because they give us a spatially resolved view of what is happening. So we can not only spatially resolve the material that has been ejected in the explosion, but we can also spatially resolve the circumstellar material that is shaped by the progenitor's mass loss prior to explosion. There are close to 400 supernova remnants in the galaxy and hundreds more in nearby galaxies. And these are Chandra images of just some of my favorite ones, but there's a long list, of course. And until recently, the most we could say about a lot of these supernova remnants is whether they come from core collapse or type 1 explosions. Of course, if there's a pulsar wind nebula present or a pulsar, or for example, the work by Laura Lopez that correlated the morphology and asymmetry of supernova remnants to whether it's more likely to be a type 1a or a core collapse, with core collapse being more asymmetric. But saying something more about the progenitor properties and explosion properties has been much more challenging. But in recent years, we are starting to connect the supernova remnant properties with the types of progenitor systems. And this is in part because of much higher quality observations and also because of progress in theoretical explosion models that allow us to interpret the data. So I just want to show you here what a basic structure of a supernova remnant looks like. So just to give you an idea of when we look at X-ray observations, what are we actually observing? And on the right is this amazing Chandra X-ray image of CAS-A, showing the various ejecta lines that are listed on the bottom here. And this is the diagram of the basic structure of the remnant. So we have the supernova blast wave. You see my mouse when oh, you do, okay. The supernova blast wave expanding into the surroundings, and the blast wave is shocking circumstellar material that has been shed by the star prior to explosion. And on the inside is the cooler supernova ejecta that has not yet been reheated by the reverse shock. When the reverse shock forms, it will propagate towards the center, reheating some of that cooler material. And the emission that we see in X-rays is the reverse shocked ejecta that is seen in this orange color. So for example, when you look at this image of CAS-A, we are seeing the forward shock in blue, and then all of this colorful emission in the shell is the reverse shocked ejecta material. A subclass of core collapse remnants contain pulsar wind nebulae, and a pulsar wind nebula is produced by the rotational spin-down energy of the pulsar, and it generates a high-speed wind of relativistic particles that is accelerated in the pulsar. These particles are accelerated in the magnetic field, and they emit synchrotron radiation. And this, of course, probably the most famous example is the Crab Nebula, and you can see the detailed Chandra image of the in X-rays of the Crab Nebula's torus and jet structures. And this, you can think of this nebula as a low-density, high-pressure bubble that is expanding inside the supernova remnant, and it drives a shock into this innermost material. Eventually, the reverse shock will reach the pulsar wind nebula and begin interacting with it, and I'll show an example of remnants that are in that stage of evolution later. But what we call these composite supernova remnants are those that have the standard sort of supernova remnant shell, but also have a pulsar wind nebula. And this is one example of the remnant G11.2 minus 0.3, where you see the emission from the shell in X-rays with a pulsar wind nebula in the center. And the reason that I like to concentrate on studying these types of remnants is because the presence of the pulsar wind nebula can actually be leveraged to constrain particular properties about the supernova remnant and its progenitor. So this is one of my favorite remnants, G292, and I will use it. It's probably one of the most studied remnants in the supernova remnant community. And it has been studied by many authors, and I will use it as an example to show you what types of methods and observations we use to constrain the properties. So this is the beautiful Chandra image of G292. You see this network of colorful filaments that represent the reverse shocked ejecta. There is also emission from the circumstellar material on the outside. And you'll notice here that the progenitor mass range that has been estimated for G292 in the literature varies significantly, anywhere from between 13 and 40 solar masses. And the reason for that is because it depends on what type of ejecta emission is sampled, where it comes from in the remnant, whether it's been decomposed from the circumstellar material. And the estimates here are mostly coming from measuring the abundance ratios and comparing them to nucleosynthesis models. And there's a lot of uncertainty in those types of comparisons, especially when we don't know what stage of evolution the remnant is in and what fraction of the ejected material has been shocked. This is a study that basically separated the very large remnant into a lot of little tiny regions and extracted spectra and measured abundances in each of those regions. And this is, of course, only possible with very deep, detailed observations. And what this study finds is a total mass of about anywhere from 1 to 2 solar masses of oxygen, neon, magnesium, silicon, sulfur, and iron, and about 14 solar masses of circumstellar material emitting in this remnant. So this is an important constraint for determining what evolutionary stage the remnant is in. And another component that is very important is how the pulsar wind nebula is evolving. So I will show you on the next slide hydro simulations of the evolution of this remnant that have been constrained by these X-ray observations. And one very important input to those simulations is the motion of the pulsar in this supernova remnant. So if we zoom in in this region here, you will see the pulsar wind nebula emitting in X-rays. And there's a pulsar embedded there, and the motion of the pulsar was measured by long baseline Chandra observations, I think in this case about 10 years apart, and it was found to be moving at about 600 kilometers per second. So now we take all of that information and constrain the hydro model for the evolution of a pulsar wind nebula inside a supernova remnant. And so in this simulations, we have the circumstellar material mass measured from the Chandra X-ray observations. We have the pulsar velocity, and I'll play the simulation to show you how that works. And we're comparing it to this radio image that shows the outline of the shell and also the extent of the pulsar wind nebula in the center, which is in green. And the explosion center is the X, and here's the current location of the pulsar. So I'm going to play this, and what you will notice is that as the pulsar is moving to the southeast. You see the forward shock on the outside, and the pulsar wind nebula is being carried with the pulsar. But because it has not displaced from the center of the explosion site, the reverse shock interacts asymmetrically with that pulsar wind nebula. So what we have when we stop the simulation at the present age of about 2,500 years, what you see is this supernova remnant shell. The pulsar wind nebula is in the center. It is basically where the reverse shock is, because the reverse shock has crushed it, but the pulsar is displaced from the center of the nebula. And the only way that you can have the pulsar be displaced significantly from the center of the pulsar wind nebula is through this reverse shock interaction. And so what this shows us is that all of the ejecta in the remnant have been shocked. So this gives us this information about the evolutionary stage. So now we can go back to the abundance measurements in the X-rays and assume that that represents most of the ejecta. And that's the key to know what nucleosynthesis models we should compare the results with. All right, so that's what I'm showing on this last slide here. This is now expected abundances in those elements that were measured with Chandra as a function of the zero age main sequence mass of the progenitor. And the measurements are the green band, and here's what's expected from the explosion models. And you will notice that the area where they overlap is a region of between 13 and 16 solar masses from the progenitor. And the simulation, in order for the reverse shock to come back to the pulsar wind nebula, we need to have about 3 solar masses of ejecta. And that is way too low to be explained by a single progenitor model. This is what, for a single progenitor, the mass that would be expected is more like 10 solar masses. So what this is telling us is that this is likely this was likely a stripped envelope explosion. Another very interesting thing that comes from these when we're able to map the abundances across the supernova remnant, the study that I showed previously was actually able to map the abundances with respect to solar for a number of elements across the supernova remnant. And what they found is that when they compare the ejecta distribution between the different regions of the remnant, they find that most of the mass is in the northwestern hemisphere for a lot of these elements. And this is a result that is expected if and I should mention that the pulsar is moving to the southeast. And because the mass is distributed opposite of the motion of the pulsar, it's consistent with simulations that show that the asymmetries in the ejecta dominate over the non-spherical neutrino emission in accelerating neutron stars. And there's really nice work by Tyler. I don't know how much he will talk about this later in his talk, that shows that a similar results for a number of other remnants. Tyler did a very detailed work for Castro showing this for various elements, but for some of the other remnants, the only way we can really do this is by looking at the bulk of the X-ray emission. And when looking at the bulk of the X-ray emissions, that may be tracing all of the ejecta, but there are complications because we might also be capturing asymmetry is in the circumstellar material. So ideally, this type of work should be done by basically mapping the ejecta distributions and the different elements in detail. But this is only really possible to do with observations that are deep enough to do those types of studies. Okay, so I now want to tell you a little bit about what happens as these remnants continue to evolve to later evolutionary stages. These are just some examples of these composite remnants of pulsar wind nebulae and how they appear later on. Most of these remnants that I'm showing here are on the order of 20,000 years old. And what you'll see is that the pulsar wind nebula no longer appears symmetric. It is displaced significantly from the center of the shell, and the morphologies are very complicated. They're very complex. They don't show the torus and jet structures. And the reason for this is because the reverse shock has completely disrupted the pulsar wind nebula. So I just want to show you how that works here. This is another hydro simulation of this remnant G327. This is a radio shell, an X-ray pulsar wind nebula with a radio emission from the pulsar wind displaced to the side here. And if I play the simulation, the pulsar is moving to the north, and there is an ISM density gradient. And what happens is that because of the combination of the pulsar motion and an ISM density gradient causes this asymmetric interaction of the reverse shock with the supernova remnant. So the interesting thing that happens, you have this trail of emission that forms with its orientation being the combination of the motion and the ISM density gradient. And then the bulk of the pulsar wind nebula emission is sort of carried away by the reverse shock and swept away to the side. So you can see that the morphology very closely resembles the supernova remnant, but what we need to do these types of simulations are detailed measurements of what type of ISM density gradient we have, as well as the precise motion of the pulsar. And it is very difficult to determine the progenitor properties of these evolved supernova remnants because the thermal emission from the ejecta is quite faint. And so this is that same remnant showing this is the emission from the swept up ISM. But what you see in the center here is thermal ejecta emission that has been mixed in with the pulsar wind nebula material, but it is quite faint. And a lot of these evolved remnants show that thermal emission, but it is very difficult to get the abundances because we don't get a lot of photons from that region. And so, of course, in the contents of the types of measurements that I just talked about, AXIS would bring an incredible improvement and allow the sort of detailed measurements that I just showed for a larger sample of supernova remnants in the galaxy. So this is a plot from that same white paper that I mentioned. It shows the simulated uncertainties for metal abundances with AXIS and how they compare to equivalent exposure time observations with Chandra and XMM. And then you will notice that there's an order of magnitude improvement in the uncertainties in the same exposure time. So the combination of the high sensitivity and high spatial resolution would allow accurate measurements across the field of view for the abundances. It would allow us to map the ejecta distributions that we can compare to explosion models. And really doing these types of measurements on small scales is key because it reduces the confusions from the line of sight circumstellar material that significantly affect the abundance measurements. We could also map the circumstellar material structure, which significantly impacts the evolution of the supernova remnants, and of course characterize the fainter thermal emission in these evolved systems, which we're not currently able to do unless we have like a minimum of 500 kiloseconds, even for some of the brighter examples. And Chandra has been extremely valuable in measuring kinematics of supernova remnants and pulsar winds, as well as motions of neutron stars. And AXIS will provide such measurements with much shorter exposure times. And there is an incredible opportunity to couple the Chandra observations, thank you, to couple the Chandra observations with future observations with AXIS, which would provide the very long baselines that would be required to measure the energetics for a much larger sample of supernova remnants for which we may not be able to do this right now. Another result that I wanted to share in the last 5 minutes is about the combined X-ray and infrared study of CAS-A. This result is quite recent, and it demonstrates how the high-resolution X-ray observations can reveal structures and inform us about the interaction between the supernova remnant shocks and the surrounding material that allows us to compare that to explosion models and learn about the explosion. I'm sure you've seen this throughout the workshop, but this is the CAS-A image with Chandra. And what I will show on the next slide is the image from JWST. Here we have as I mentioned, the main shell of material that has been reverse shocked. And this is the high energy synchrotron radiation from the forward shock. And then I'll move to the infrared image. This is what CAS-A looks like with JWST. I'm sure you've seen this before. Again, we have at the longer wavelengths, we have the warm emission from dust at the forward shock. This is a shock CSM. We have the main shell. We have the main shell here in the whitish color, but then there's this region in the center that Danny Milisavljevic calls the green monster. I think now it's stuck, but so it appears green because it's emitting primarily in this this 12 micron filter that it's dominated by warm dust. And at first we didn't know, we weren't sure if this is something that's along the line of sight or if it's interior emission from the supernova ejecta. If I zoom in, we notice these structures these circular structures that we have not seen before in CAS-A and that are very distinct. And it was unclear what was producing these and where this emission comes from. And the main crucial clue came from the X-ray observations. This is now the Chandra X-ray emission from CAS-A. And this is the combined X-ray JWST and HST optical. We already saw this image earlier. And you will notice that even though the X-rays don't show those circular structures, there is X-ray emission coming from that green monster structure that can be correlated. So then a detailed analysis of the X-ray spectroscopy from those regions in comparison to regions that we definitely know are coming from circumstellar material revealed that emission is actually circumstellar material. And the properties of the regions here and the regions along this green monster are very similar. So the X-ray observations revealed that this is circumstellar material that is actually in front of CAS-A. So then the question is, how are these holes produced? And I want to show you a very recent results from 3D hydro simulations of CAS-A. This is showing the surface of the forward shock interaction region. So where the forward shock is interacting with the circumstellar shell. And there are hydro instabilities that form these protruding ejecta fingers. So then when you look at the simulation of what you would expect the morphology of the circumstellar shell would be at this surface, you get this. So it's basically those protruding ejecta fingers are forming these circular holes in the circumstellar shell. And the morphology is very, very similar to what we're observing. So I think this highlights the power of complementary high-resolution deep X-ray observations combined with other wavelengths in understanding these complex structures that arise when the supernova interacts with the surroundings. So I think I'm definitely out of time. I think it's safe to say that X-ray observations of supernova remnants have really revolutionized our understanding of these systems and how they evolve and what type of progenitors they come from. And AXIS would provide an incredible leap forward in connecting many more supernova remnants to explosion properties. Currently, we're only able to do that for a subset that have very deep observations, but I think really the future, in my mind, of this field is to be able to do this kind of work on a population level, so that we can actually type the remnants that are most of the remnants in the galaxy and be able to constrain their properties and then compare with extragalactic supernova observations. I'll stop there. Thank you.
Thanks. We have time for questions. Mike.
That was a really nice talk, really nice images. So I'm wondering about in really low metallicity systems like, dwarf galaxies or other things, how would the supernova remnants kind of be different and how in their evolution and how would they look? I'm just curious, like when you go down to really low metallicities, how they would be. Yeah.
So metallicity would be one of the parameters in these evolution models that will impact the expansion of the supernova remnants into the surroundings. So we haven't yet simulated these with the hydro observations, but that could certainly be done as a function of metallicity as well. They would probably tend to be larger and more extended for similar ages. That could be done. So currently we have supernova remnants in the Magellanic Clouds I've studied quite a bit, but we haven't yet done these types of hydro simulations to understand them on a population level and what types of progenitors they come from. It's only done for a few of them. But that's certainly something that can be done. And if we had, of course, like much deeper high angular resolution observations for remnants in a resolved way for remnants in the Magellanic Clouds, we could do this type of work. Currently, it's just a handful for which we have more information than just type 1A or core collapse.
Can I ask a little bit about the simulations do? I mean, it's gorgeous modeling and
Yeah.
it maps very well to the data. So what's the sort of minimal kind of physics you need to put in? I mean, pulsar wind nebulae, of course, are very strongly magnetized, and you can even start to imagine things that are beyond MHD,
Yes.
electrodynamics. So can you get away with just pure hydrodynamics, or how far down the rabbit hole do you have to go?
That's a very good question. And I think, so sort of my answer is we are, like the next step in these simulations is to use MHD because it is really important in understanding the structure of the pulsar wind nebulae, especially in these evolved stages. In terms of just with the evolution, like for example, what I showed in the simulation where you just get a displaced pulsar wind nebula bubble that is basically outlines where the reverse shock is. I think on that level, HD does okay, but when we, and I didn't get to show that in detail, but a lot of these pulsar wind nebulae, especially in the late stages, show these very complicated structures and outflows and that are clearly magnetic. And in order to really do the physics of the pulsar wind nebulae with these simulations, we absolutely would have to do MHD.
That'll be a lot of fun. Yeah, great. Any last questions? Yeah, all right.
So I had a question about determining whether a pulsar wind nebula is in a supernova remnant. I mean, you showed, I'm sure there's like some spectral decomposition that goes into all of this, but like, sometimes it looks just from your images that it was kind of a little messy. And I was wondering, is that something that AXIS with its higher signal to noise will do better than Chandra? Is there like a question about how many supernova remnants have pulsar wind nebulae in them, and is that something that AXIS could help with?
I mean, yes, absolutely. Finding, I guess I put this on the last point here, detection of these systems in young supernova, both supernova remnant, detections of supernova remnants that are fainter and pulsar wind nebulae would be extremely helpful. I assume that Oleg will touch on some of this, but the other thing that Axis would be extremely helpful with is doing the sort of pulsar wind nebula physics that we cannot currently do for a lot of these systems because of the lack of sensitivity that we would require. Like you saw that beautiful image of the Crab Nebula that shows the structures very clearly, where we can study the spectral changes and the aging of the particles. But for a lot of these, we just don't have, even with deep observation, we just don't have the depth that in order to be able to do that. And it's and certainly there is a variation in how bright these pulsar wind nebulae are. So I think that it would, looking for signatures of these pulsar wind nebulae in a larger population of remnants would probe the question of like what fraction are type 1a or core collapse, even because we only even know that for very like a limited subset of the total number of remnants we have in the galaxy.
Great, thanks. Well, let's thank T once more. We're getting good at this now. We can do it. Okay, so the next speaker is Daniel Castro, who will be talking about synchrotron filaments in supernova remnant shocks.
Well, hi everyone, and thank you very much for having me. Thank you especially to Thea for that introduction to supernova remnants. I could skip over a lot of the things that I was going to say. And I usually overspeak, so that's a good thing for everyone in this room. So I'm going to concentrate on the connection between supernova remnants and cosmic rays, and cosmic ray acceleration at the forward shocks of supernova remnants. There are many reasons why you should care about this connection for many different areas of astrophysics. I've listed a few of them here. I'm not going to go through all of them, but we have recent results from galaxy evolution simulations have shown that cosmic ray feedback is actually a really important component into how galaxies look and how they evolve. So that's just a piece of the puzzle, and cosmic rays, understanding them and how they get accelerated within our galaxy is a really important piece. Route. So, what evidence have we gathered up to now that supernova remnants can accelerate particles to cosmic ray energies? Indirectly, it's been shown that the shock structures are actually changed by cosmic ray acceleration by a sort of significant amount of the kinetic energy being placed into accelerating cosmic rays. But aside from that, we've also gathered some more direct evidence, and a lot of it has come from non-thermal X-ray emission. So just the detection of non-thermal X-ray emission from the forward shocks of supernova remnants already indicates that you have TeV cosmic ray electrons being accelerated at the forward shock. But also, the sort of from those synchrotron filament observations, we can derive a magnetic field strengths, and it's been shown that those magnetic field strengths point to magnetic field amplification by the forward shock, and that can really be only explained efficiently by the acceleration of cosmic ray forward shocks. And finally, of course, gamma ray emission detections of supernova remnants, which had been detected for a long time with Cherenkov telescopes and other missions, but the Fermilab has really revolutionized that. So I'm gonna really concentrate on synchrotron emission in the X-rays, because that's really the point of this talk today. It was first detected by Koyama et al. In 1995. This is not a picture of that. That was an ASCA observation. This is a Chandra composite image where the red is showing you mostly thermal emission from SN1006. and the blue is showing you emission that is most definitely not thermal in nature and understood to be synchrotron emission from relativistic electrons spinning around a very strong magnetic field. Um, Now, we can connect that synchrotron emission to the magnetic field strength in several ways, especially because the stronger the magnetic field, the stronger the magnetic field strength is, the faster your accelerated electrons are going to lose their energy through synchrotron emission. And variability studies in remnants like RxJ 1713, here shown by in a paper from Uchiyama et al. In 2007, show that this is basically nuggets of synchrotron emission in supernova remnants can appear and disappear in this timescales of years or less, and that actually and from that variability, you can actually derive magnetic field strengths upwards of half a millisecond to 1 millisecond. Sorry, half a milligauss to a whole milligauss, which is implies amplification factors of hundreds in comparison to what the ISM magnetic field strength is expected to be. A little bit more simply, you can also connect the width of the filaments themselves to the magnetic field strength. So basically, your electrons only have a certain amount of time, and as they advect or diffuse away from the shock, they will lose their energy through synchrotron emission, and thus you can connect the magnetic the filament width to the magnetic field strength that is being amplified or compressed and amplified by the magnetic by the shock itself. Here I'm showing you some results for Tycho, Kepler, and Cassay done by Bamba et al. In 2005. And these are images in the very hard energies from Chandra. Now, I'm going to be talking to you about some recent work that we've done with Chandra, where we've tried to measure both the filament widths and the velocity of the filaments, and I'll show you why that's kind of useful and interesting. So let's start with Cassay. You have the beautiful Chandra picture of Cassay, only in the very hard band. And I'm pointing in little boxes all the filaments that we derive the widths and the velocities for. And I'm showing you just one example of one of the filaments that we derived and how it changed in position between 2004 and 2019. You can derive the proper motion of all of those filaments and also the filament width of all of them, and then plot them just like this. You have width on your y-axis and velocity on your x-axis. And it turns out that you have two different competing processes for the displacement of your electrons that are being accelerated. They can be either advect away from the shock or diffuse away from the shock. And the two lengths of those processes, or the two widths that are derived from those processes, are tied to the magnetic field, but one of them is actually dependent on the velocity. That's just advection. And since in this case, we can see that the width of the filaments increases with the velocity of the shock, we are going to, this suggests in this case that the advection length is really the dominant process here in the case of Cassay for the velocities of the Cassay filaments. Secondly, RCW86, we redid this. This is just the northwest part of it, and I'm showing you one example of specifically the one that is pointed as a number 1 there of its displacement. And when you do a similar analysis than what we did with Cassay for this one, we only have 3 filaments, as I mentioned. But the behavior of the width versus velocity plot is completely different, and this suggests that it's either not advection or that it's just diffusion, or that we don't really have enough information. And that later on I'll talk about how axes can contribute to that type of analysis. And then finally, I'm going to show you HES 1731. This is, again, just the northeast part of that remnant. We did a similar analysis to it. And again, all the filaments were very close in velocity and in width. So it's kind of hard to tell between the two scenarios. I'm not going to go too much into detail about what the results of those studies yield from the Chandra stuff, because I've already gone with it through them in words. But I'll show you a little bit of what the role for axis will be in this type of study. So in the upper right, I'm showing you a figure from Brian's paper in 2011 of XMM observations of RCW86, where you can see that the blue stuff, which is the hard emission, is it seems fairly diffuse, and it's hard to tell that it's really, really for sure thin filamentary structures. And then when we observed this in 2013 with Chandra, we showed that you had this not only filamentary structures within the main shock, but also filamentary structures ahead of the shock. This is the type of study that would really benefit from axis observations, also because this is really an image of a mosaicked Chandra observations of RCW86, which conveys that it's actually a fairly big supernova remnant. And an axis-like instrument would certainly help us mosaic such a remnant and use its flat PSF as a tremendous tool in order to gather really consistent information all across a remnant like this one. This one is HES J1713. Again, it's a huge remnant. That was a mosaicked 3 pointing image from XMM. And here I'm overlaying what we've done with Chandra. It turns out that the Chandra observations show this emission to be very, 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 very faint. It's completely non-thermal, apparently. And in order to understand a supernova remnant, you really need to leverage the high, sort of the huge collecting area that an instrument like AXIS would provide us with, and possibly even find a thermal emission in a remnant like this, which would really help us understand it fully. And finally, with CAS-A, I'm just going to show you sort of, I did some simulations about what AXIS would do with CAS-A in the sort of the very hard band, sort of 4 to 10 kiloseconds, and roughly you would need about 10% of the time that you need with Chandra in order to get the same results in the synchrotron band. Now, why is this interesting? Well, first of all, before I even go into this, top left corner of that image, which is commonly seen by everyone, looks very nice and tight and filamentary. And the bottom right picture of CAS-A actually looks a little bit more diffuse. And you will now notice that in every single image that you see from CAS-A by Chandra. It turns out that the optical axis is roughly where the upper left corner of that orange box is. So the further away you get, the worse the PSF gets significantly. This would, an observation with axis would certainly help us do similar, very sort of high resolution analysis, both spectrally and spatially, all across a remnant like Cathay with a single pointing rather than having to repoint the thing to point the optical axis on every single filament that you're interested in, which is really unrealistic. And here I'm just showing you a plot about how the index changes across a single filament. And the bins are roughly half an arc second here, and you can see how the index becomes steeper as you move away from the shock, and this is going to help us with more detailed physics about this. People will suggest that maybe it's not that the magnetic field strength is amplified, but that you have magnetic field dampening as you move away from where the shock is. So it's really the magnetic field shape that is giving you the width of these filaments. And observations with axis would certainly help us sort of telling those two scenarios apart much better. Thank you.
Great, thank you very much. We have time for questions. Yeah, Mike.
Really nice talk, and man, these simulations, these are great. So, in terms of understanding this system in the filaments, like, where do you get the most important information? Is it kind of from the edges, or are you trying like to understand what's actually going on?
So certainly I mean, most of the information you're going to get in terms of the synchrotron filaments, it's going to be from the stuff that is in the outer regions.
Right. I got this wrong. Yeah.
Mostly because you can tell that the width of that filament is really related to the observed width of the filament is closer to the actual width of the filament, leaving projection effects aside. If the filament is closer to the center, so for example, if you had a filament that is, coming at you, in that case, the width of the filament is very, very difficult thing to like suss out from your observation. So in this case, it would definitely be the stuff on the most outskirts of a remnant like this.
So, I mean, following on from that, there's some expectation for electron precursors on there ahead of these shocks.
That's right.
Has that been seen with Chandra, or is there an expectation you could see that with Axis?
Yes and no. So it's a difficult geometric problem, right? Because you will have a certain width of the filament, both ahead from the peak and sort of behind the peak, because of the line of sight sort of composite of a thing that is not actually a shell, but it's instead of a shell-like sort of sphere. But yes, from the fusion, you do expect a precursor. So you do expect some of the cosmic rays to actually move ahead of the shock, because they need to do this in order to recross the shock several times after they sort of they disperse. I believe that optical observations have been able to do this with the Cygnus loop, which is huge in the sky. Axis could. I haven't done simulations to show this, but if somebody would have a chance, it would be something like Axis because of the collecting area and just the ability to, not because of the angular resolution, because still if you want Chandra can best it at that, but it's just these things are very faint.
You need the counts. You need the Seals noise. Yeah. No, thanks. Okay, let's thank Daniel once more. Okay, so our next speaker is Oleg Kargaltsev, who will be talking about advancing the frontiers of pulsar wind nebulae. So, and I'll give you a 2-minute warning after this.
Thank you. So thank you for the opportunity to present here some of the highlights of what Axis can do for pulsar wind nebulae. This is not a review talk, and I'll just show, as I said, a few highlights. And these are sort of picked based on my personal preferences and also preferences of Samar Safi Harb's group at University of Manitoba. So first, let's just briefly recall, and thankfully, Thea already presented a few important things about pulsar wind nebulae, but I think one thing that I can say is that if, let's say, NASA likes putting certain objects into boxes, then if there is a stellar feedback box, then pulsar wind nebulae can be put there because they do kind of inject in the interstellar medium a lot of very relativistic particles, electron positrons, as well as magnetized wind, so basically injecting magnetic field as well. In brief, pulsars can be thought about like extreme accelerators, just like powerhouses that produce particles reaching in energy PeV range, as well as antimatter factories, right? Because they produce presumably in equal amounts, positrons and electrons. And so because of all that, they are sort of ultimate high energy astrophysics plasma laboratories, right? Now, this was all like very general, but there's few key fundamental topics one can study with pulsars and pulsar wind nebulae. These are particle acceleration mechanisms, such as collision and shock acceleration or reconnection in relativistic wind. Then the outflows, so the magnetized outflows we heard a lot here, right? The AGN jets are magnetized relativistic outflows. So pulsar winds is just another example, which is actually closer to us, and we can sometimes see much more details of what's going on. Then there is this particle escape. They eventually, the pulsar wind particles escape into interstellar medium, and then there's very interesting things happening, as you will see shortly. And finally, of course, pulsar wind nebulae structures actually, and their interaction with supernova remnants, as you heard from Thea, they can tell us about neutron star kicks and actually also about the progenitor star, right? So now why pulsar wind nebulae really had this revolution in terms of learning about them since the launch of Chandra? Because primarily of three reasons, and this revolution is demonstrated by a number of papers over there as a function of time. So the primary is, of course, angular resolution, but one should not also forget about these capabilities of performing spatially resolved spectroscopy with ACEs, right, on the essentially arc-second scales if there is enough signal to noise. And finally, there's one more thing, maybe not so like much mentioned, is the very low detector background that really enables studying many pulsar wind nebulae that would be too faint otherwise at higher detector background. And so I think that's where kind of AXIS can actually make some advances over Chandra. So the resolution is of the order of arc-second, so it's good enough, as you will see, for many things for pulsar wind nebulae, and it will also deliver higher effective area, which means we can measure much more accurately the spectra. So here is just basically the choices I made, and some are for particularly interesting kind of case studies. And if you want to know more about the larger population, you can look at the poster by Cés Gagnon over there. And so let me just like briefly go over this case study. So the Vela pulsar wind nebula, in my opinion, is actually one of those nebulae that can drive the whole field forward. And Crab is very often mentioned, but in some sense, Vela is actually better and actually more interesting system than Crab. I don't have time to argue. That would take for this like 10 minutes. But very briefly, it is actually accessible to XP polarization measurements. It's a cleaner system because it's in closer and in larger remnant. So there's not so much overlap between remnant emission emission and the nebula. There's interesting interaction in the remnant. It's a multi-wavelength object and so on. And there is one more interesting aspect about the Vela pulsar wind nebula is the dynamics that we can observe on time scales of days, essentially. And this dynamics is kind of interesting because it is actually one of the dynamical features is this corkscrew-like rotating jet. This is an assumption that it is rotating. Basically, I'm trying to say that it might be precessing with the neutron star. And one other interpretation is that it's just like instabilities that look like rotating jet. So I'm going to basically leave it up to Axis to verify which one of the two is correct. And below is a little movie of free precession. Win can tell us if it applies to neutron stars or not. Yeah, so there's support from other objects now with deep Chandra observations of seeing these corkscrew patterns in the jets. And this is jet from a different pulsar wind nebula. You can see the arc-second scales there, right? 10 arc-seconds. So it may be that Axis can still see this kind of structures at its angular resolution. Now, what Axis definitely can see is this large-scale fainter structures, and this is a different case of a pulsar wind nebula where the pulsar escaped from that supernova remnant that you see over there in the corner. And so what's happening is unexpected. You will behind the moving pulsar, right? That's just hydrodynamical effect. But this sideways outflow is was something of a biggest surprise. And apparently, there is a escape from the apex of the bow shock of the most energetic particles that is happening. And these particles kind of move in the interstellar magnetic field and light up the structure of that field, but they might at the same time modify the magnetic field. Right, just like cosmic rays escaping in supernova remnant shocks ahead of the shock can modify magnetic field. Why do we know that these most energetic particles are escaping? How do we know that? You'll hear about this object a bit more from Noel Klingler, but I'm just going to show that if you do a color image of higher energies versus low in Chandra band, then this outflow is blue, while the tail is actually red. So it's a proof. And that's where the spectroscopy is the key. And in order to actually see if the magnetic field amplification is indeed happening, for example, we do need to map out this, obtain a spectral map out the spectral structure of this outflow, which is not really possible with Chandra yet. Or it requires megaseconds of exposure, but should be possible with Axis. Simulation is in the middle. This is an older type of system where we have pulsar again. In green, you can see X-ray emission, and blue is TeV, and radio is in red. And so what's happening here, there's something interesting. This is offset TeV emission, which may be what Thea explained to us, this relic nebula pushed to a side by the supernova reverse shock. But then there is this X-ray structure, which does not follow the TeV structure, which one could expect in the hydrodynamical interaction model. And that's maybe what Chris asked Thea about, whether there's non-hydrodynamical or more complex effects are important. And so potentially here, this more recently produced electrons that radiate X-rays, they are actually sort of diffuse out anisotropically, while the relic nebula that was displaced earlier to south was a hydrodynamical interaction. This is the case of a system which is young, and where this interaction with reverse shock is still maybe ongoing, and there are these very interesting structures that you can see, fingers of the hand of God, that is probably a result of this interaction. And so here is a simulation done by University of Manitoba group, by Samar's group, which actually shows that we can gain a lot. For example, here is 350 kilosecond exposure with Chandra. You resolve the termination shock now in some of this interesting structure, which you can kind of see in 50 kiloseconds of Axis simulation. And of course, you can study all and map out the spectral structure of that larger nebula. And here is a demonstration of how much improvement one could gain for different elements of the nebula, comparing Chandra and axis for the same exposure. So you see how the contours shrink. A very different maybe, or maybe not, type of wind nebulae is a magnetar wind nebulae, which we only know very few, right? And so this is the one around J1834 magnetar, which went into a flare, and that's how we recognized that it is a magnetar nebula, because otherwise it was just like a faint extended blob of emission. And there can be many things like this in the galaxy, which may be these dormant magnetars that only occasionally go into an outburst, older magnetars, because there should be more older magnetars than younger ones, right? And so that's the potential for one of the things that AXIS Galactic Plane Survey can do is to find those objects. There is also seems to be interesting energy dependence for this magnetar wind nebula, which might change spectrum on very kind of small scale, which might be related to magnetic field strengths there. And as you know, magnetars are very magnetized neutron stars, but you really need axis XMM, which you see here, cannot really do those scales, right? And so that's another object that is we thought is a pulsar in Remnant that actually went into a brief flare, and there is a little tiny nebula around it. For some reason, it's not as Crab nebula. Thank you. And it may be because it's strongly magnetized pulsar, and the nebula may have also brightened as a result of the this magnetar activity, but it's kind of difficult to understand this with Chandra, just like a limited signal to noise. But again, if you do a simulation and compare of how that would look like if AXIS observed it, you'd see that we could get much better measurements of the spectrum and actually how much the flux changed. So I'm wrapping up with my presentation. But this is a picture of the galactic plane survey from the white paper that is out there about AXIS. And I think what we can expect here is to look for many fainter pulsar wind nebulae to increase significantly population of known pulsar wind nebulae detected in X-rays, including magnetar wind nebulae. But we also may find this interestingly variable pulsars that sometimes are magnetars, and they actually might have faint X-ray nebulae around them, and that may be a way actually to find them. So I'm just going to leave you with conclusions where I say that Chandra has demonstrated very convincingly the potential of high-resolution imaging for pulsar wind nebulae and of spatially resolved spectroscopy. And so AXIS will definitely, I think, conduct a very informative studies of those known nebulae by extracting much more science from there. And but it will also do a lot for population. And let me just leave you with that. And also this synergy, which I didn't have time to talk about a lot with other wavelengths, but you could see some of the radio images, like for the hand of God there, and TV emission that I showed. So the synergy is going to be definitely there. Thank you very much.
Thank you. Yeah, these are beautiful objects. Mike.
Yeah, so I'm wondering, I think Samar was talking about this at some point, but you know, you have these TV sources that we don't know the counterparts from.
That's right.
And we're within our like galactic plane survey, what like potential do we have to figure out, you know, if those sources might be something associated with, you know, pulsar wind nebulas, you know, faded, or I don't know, supernova remnants, some other source like that. Is there a potential there, or?
Yeah, thank you for your question. So the one way AXIS can contribute to this is basically to discover potentially new pulsars with by resolving their nebulae. So there's going to be this faint, looking like something like this, perhaps. This is a magnetar, but there are pulsar with nebulae that look like this. Or maybe you can look even at this picture. So if you have a TV source, and then next to it, you have something extended. There are not so many non-thermal extended objects in our galaxy, really, right? So if you see something like that, some kind of blob which is non-thermal sitting next to TV source, it might be that you have actually a middle-aged pulsar there, which hasn't been discovered in radio or gamma rays. There are such pulsars actually. And the pulsar itself can be pretty faint compared to nebula. So you really just like seeing this extended blob is a good hint that you have a middle-aged pulsar, and if this next to a TV source, it's a good hint that TV source is powered by a pulsar. It's a relic nebula of that pulsar.
Last question. Great. So the current galactic plane survey and the bold survey is fairly tight on the galactic plane. I was wondering what would be gained for Pulsar Wind Nebula and Magnetar Wind Nebula if we did a better survey of the bulge, maybe in GO time as opposed to GT time, maybe not going quite as deep, but covering a wider part of the galactic bulge.
Well, thank you for your question. So I think there's some kind of optimization that needs to be done here, and maybe it's not quite done. The bulge is not really the place to look for pulsar wind nebulae because it is more of an older population. And so for pulsar wind nebulae specifically, the galactic plane itself, these regions along the plane are better. And so the longer this coverage of galactic plane, the better it is for pulsar wind nebulae science. But on the other hand, you know, the bulge has its own interesting objects like binaries that might merge and produce gravitational waves. And also actually some of the millisecond pulsars, the old recycled pulsars that can be there, they actually can have faint X-ray nebulae. For example, Black Widow does have its famous pulsar. So we might find something unexpected in the bulge as well for pulsar.
Great, thanks. Well, let's thank all the speakers of this session again.